Hi there, welcome to this course on secure coding. First of all, a little bit about myself. I am an electronic engineer. I deal with IT security and digital forensics. I have achieved various IT certifications such as the EC Council CEH, EC Council CaseNet, Certified Application Security Engineer.net, and other certifications. I would like to begin mentioning some cybersecurity laws and guidelines because they are a framework within which the development of applications fits. These are the GDPR, the ISO 27001, the European NIST Directive, and the AIC 62443. That's the standard for the security of industrial automation and control systems. Other important standards and acts are the COBIT for IT governance, PCI DSS, HIPAA, SOX, FISMA, and the PSD2. In modern application design, it is important to think about safety and security requirements right from the design phase. Fundamental for security is also the choice of the framework with which to develop the applications. In fact, modern frameworks offer native protection mechanisms and implicit security checks. The availability requirement is typically guaranteed through redundancy mechanisms, for example by implementing RAID systems for storage disks, replicas at the DBMS level, or with the use of reverse proxies for web applications. Integrity is obtained by using hash algorithms such as SHA-1 and SHA-2. Confidentiality is guaranteed by the use of encryption used on endpoints and on data in transit on communication channels, and also through the use of authentication and authorization mechanisms. Authenticity and non-repudiation pass from the involvement of a third party who typically issues a digital certificate attesting to the identity of the person to whom it is issued. The third party also acts as a guarantor in a data flow between A and B that the data actually arrive at B. Hi, welcome back to this course on secure coding. In this lesson, I will talk about recent statistics related to cyber attacks and the most common type of attacks agents. In recent years, there has been an exponential increase in cyber attacks. The first 6 months of 2019 have seen more than 4,800 publicly disclosed breaches, exposing an incredible 4.1 billion compromised records. The global average cost of a data breach for the 2019 study is 3.92 million, a 1.5% increase from the 2018 study. The most common attacks are DDoS, or attacks that use ransomware, trojans, backdoors, bunker malwares. A typical infection occurs through a phishing action with email or chat aimed at downloading and running a program that is often not the malware but a downloader for the real malware. The malware then today are so sophisticated that to deceive antiviruses They run in memory by injecting their code into legitimate running processes. In most cases, the data breaches are aimed at exfiltrating personal data of users or access credentials to accounts or financial services. Most of the attackers are people unrelated to the attacked targets, but in about 30% of cases, the attackers can be people within the target, the so-called malicious insiders. Attackers from the inside are often underestimated, with serious consequences from the point of view of security measures for the internal protection of networks. As for the targets attacked, recent statistics show a greater tendency to attack applications that are widely used by users. In fact, for user application, it is more difficult for system administrators to keep them all constantly updated with the latest patches. This slide shows some striking statistics on cyber attacks, such as the fact that the world lost around 445 billion every year due to cybercrime. This is not a periodic table of chemical elements, but a price list for zero-day vulnerabilities of a vulnerability trading company. To demonstrate the enormous interest that revolves around the world of vulnerabilities, just look at the price of how much zero-day vulnerabilities are paid. Here are some recent vulnerabilities with an indication of the CVE code of the vulnerability. CVE stands for Common Vulnerabilities and Exposures, and it is one of the best-known standards by which known vulnerabilities are identified and described. Thank you for your kind attention. Hi there, welcome back to this course on secure coding. In this lesson, I will talk about the life cycle of software development and the tools that are available in the various phases of the life cycle to increase the security of the application developed. The course will focus on measures and methodologies to increase application security, but not considering the aspects related to performance and robustness, as important as security, but not covered in this course. Testing is an integral part of the software development process. At each stage of the software development lifecycle correspond specific tests that must be carried out both to verify the functional aspects of the applications, but also to verify the adequacy of the software to the functional security specifications. The course deals with secure coding methodologies in more depth, which, however, as can be seen from the graphics, is only one of the tools available to increase application security. Equally important, for example, is to perform pen tests of applications or threat modeling in the design phase. Often, we are led to think that the main cause of the vulnerabilities is due to bugs introduced in the programming phase. In reality, as seen from the slide, there can be many causes that lead to the introduction of vulnerabilities in applications. Statistically, it has been proven that at the exit at each stage of a software lifecycle, a certain number of defects per 1,000 lines of code remain untapped, even from the last final validation phase of the software. This graph shows the change in cost inherent in correcting errors discovered in the early stages rather than the final stages of the software life cycle. Here we see a fairly shared concept of the fact that subsequent evolution of any software inevitably deteriorates its quality. Thank you for your kind attention. Hi, welcome back to this course on secure coding. In this lesson, I will briefly discuss risk analysis and vulnerability research. The first step of the risk analysis is to search for vulnerabilities on the target being analyzed. Then we need to think about the possible threats that can exploit the detected vulnerabilities, also quantifying the statistical probability on an annual basis of such exploitation. The next step is to quantify the economic damage resulting from the exploitation of the vulnerability. Once the damage quantification has been calculated, for example, $10,000, you will immediately know how much you can invest in countermeasures, up, for example, to 10,000 maximum. The risk is determined by the calculated damage and the probability of occurrence of the threat and is indicated in predetermined levels, for example, high, medium, or low. We have seen that the search for vulnerabilities plays an important role in risk analysis. Let's see how we can search for vulnerabilities inherent in certain targets. You can search for vulnerabilities manually through search sites. For example, one of the most famous sites is Security Focus for use vulnerability scanners. Let's see a vulnerability search simulate on with Security Focus. From the first combo box, you can select the vendor, then move on to select the product of interest. And at the end, you will have the list of all known vulnerabilities of that product. By clicking on a specific vulnerability from the list found, you will access details of the selected vulnerability. The first detail card of the vulnerability provides general data on the vulnerability, such as whether it can be exploited locally or remotely, its CVE code, and the versions of the vulnerable target. The discussion tab provides a brief explanation of what the vulnerability consists and what effects its exploitation can cause. In the Exploit tab, you can sometimes find a POC, a proof of concept, of the vulnerability. That is a simple program that allows you to experiment with a possible exploitation of the vulnerability. The last two tabs, Solution and References, explain where to find patches to mitigate or eliminate the vulnerability. The NIST website allows you to create graphs that show the trend of the vulnerabilities over a certain period of time. For example, in this simulation, I simulated the search for cross-scripting vulnerabilities. The CVE details site is also interesting for the search of vulnerabilities. In this simulation, for example, I simulated the search for Android vulnerabilities. Thank you for your kind attention. Hi there, welcome back to this course on secure coding. In this lesson, I will talk about the threat modeling process. Threat modeling is a methodology used in the design phase of an application to identify, based on the architecture of the application, the possible threats capable of acting on the various points of the architecture, nodes or connectors. Once threats have been identified, it is therefore possible to draw up specific security requirements and specifications to be implemented to mitigate the identified threats. Threat modeling consists of 4 phases. The first step is to create a visual graphic representation of the application. Then, in the second phase, the architecture is broken down into constituent parts, and in the third phase, the various threats looming over the decomposed architecture are identified and enumerated. In the fourth and final phase, a risk analysis is carried out for the various threats identified in order to give priority to mitigating them, choosing the most appropriate security controls to be applied. For the identification of threats, it is possible to rely, for example, on the Microsoft Stride methodology, an acronym that takes its name from the 5 possible categories of threats such as spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. There are also other methods that can be used for threat modeling. The slide shows some of them. As for the visual representation of the application architecture, one of the most used diagrams in threat modeling is the data flow diagram. It highlights the architecture of the application in terms of processes, entities, data stores, and data flows. And the preeminent emphasis is given on the data flows that connect processes, entities, and data stores together. As an alternative to the data flow diagram, you can start making threat modeling from a process flow diagram, structured as the example of the slide. In this type of diagram, the main emphasis is placed on the functional representation of the processes that make up the application. Starting from the visual representation of the application, we move on to identify the threats that exist on the individual nodes by means of input data and the entire path that can be involved by the threats. The threat path is defined as the sequence of all processes nodes that perform critical security processing. In this slide, you can find some examples of questions you can ask yourself to identify possible threats looming on the data flow diagram architecture. Then the identified threats can be classified and categorized according to, for example, the already mentioned Stride methodology. For each type of asset or target of the data flow diagram structure, it is possible to know in advance which categories of threats could theoretically act in the absence of controls, as shown in the table. Starting from the identified threats, you can then move on to expand the tree of possible sub-threats. Here is an example of creating a tree of possible sub-threats from a primary spoofing threat. The last phase, after identifying all the possible primary and secondary threats on the data flow diagram, consists in attributing a risk factor to each of them and determining the possible security controls to be implemented to mitigate them. In broad terms, the table shows the general types of mitigation corresponding to each threat category of the STRIDE model. For example, to mitigate the categories of threats included in the type of tampering, methods must be adopted to guarantee and verify the integrity of the data, therefore, for example, through the use of hashing algorithms. A simple tool that can be used to assist the entire threat modeling process is, for example, the Microsoft Threat Modeling tool, but there are also other tools that can be used to avoid a completely manual approach to threat modeling. Thank you for your kind attention. Hello, welcome back to this course on secure coding. In this lesson, I will show an example of using Microsoft Threat Modeling tool to make a simulation. So we can start by creating a new model. So we will therefore see an empty diagram in which we will be able to build the architecture of our system. Suppose, for example, we want to create a simple web architecture consisting of a web client, a web server, and a database. So let's start by adding a browser type component to the diagram, taking it from the list of graphic objects and placing it on the diagram. For each graphic element, we can configure its properties through the bottom right pane, Element Properties. This will allow for more accurate results when analyzing possible threats. Now let's add the web server element. We also add the database item, and we can use data flow connectors and then connect the browser with the web server and the web server with the DBMS. Boundary lines can be added, for example, to limit internet access, and we can add the perimeter of the internet LAN. When the structure of the software architecture is finished, you can switch to the Threat Analysis view. This view shows a list of all possible threats affecting the various components of the architecture, individual components or sets of components communicated through data flows. For each individual threat item, by selecting it, you can see its details. Its status can be changed, annotations can be added, and at the end you can also create summary reports. By default, a report in HTML format is created, and this report shows all the details of the architecture and threats detected with automatic analysis. So thank you for your kind attention. Bye. Hi, welcome back to this course on secure coding. In this lesson, I will talk about the OWASP community and the top 10 OWASP list of the main risks in the world of web applications. The OWASP community deals with various projects related to the security of web, mobile, and IoT applications, and the development of related tools and methodologies for security. This slide lists some of the main methodological and informative documents on web application security. You can find many interesting projects for the IT security world on the site, such as the Pentest Guide for Web Applications, or projects related to tools developed by the community, such as the OWASP ZAP. The top 10 OWASP of the main risks is a guide that the community has drawn up and that periodically updates, which illustrates what are currently the 10 most critical risks that can undermine the security of applications and web servers. Risks include issues related to a lack of validation of application input, vulnerabilities related to authentication mechanisms, and management of web sessions. They also detect risks due to incorrect implementation of access control authorization, incorrectness in the configuration of web server or application server, and also problems related to APIs and third-party components used without adequate security or the absence of vulnerabilities. They also detect risks on the insecure use of data exchange files, such as XML or JSON, identifying them under the XML external entities and insecure deserialization entries. Thank you for your kind attention. Hello, welcome back to this course on secure coding. In this lesson, I will talk about security static code analyzers. The security analysis tools can be divided into two categories, the SAST tools and the DAST tools. The SAST tools are static application security testing tools. The DAST tools are dynamic application security testing tools. The SAST tools take the source code of the applications as input, analyzes it, and detect possible vulnerabilities or bugs in the lines of source code. On the contrary, the DAST tools analyze the running application and through various tests, mainly consisting of data inputs sent by request to the web application, they try to detect the presence of vulnerabilities by analyzing the relative responses. Among the SAST applications, it is worth mentioning the checkmark solution, present in Gartner's Magic Quadrant, supports the analysis of code developed in various languages, including Java, C#, PHP, JavaScript, C++, Perl, etc. It complies with various standards, including OWASP Top 10, OWASP Mobile Top 10, SANS 25, HIPAA, FISMA, PCI DSS, etc. Another valid SAST tool is that of Synopsys, also present in Gartner's Magic Quadrant. The SonarQube tool can also be mentioned, which in addition to doing static analysis in terms of researching security vulnerabilities, also performs an analysis on the quality of the code in terms of programming inefficiencies. Once the code has been analyzed, SonarQube generates a web project that shows the result found, categorizing them into three types: bugs, vulnerabilities, code smells, and indicating the number of results found for each category. Of each result, you can see the detail, which indicates the severity of the result, and the file and the line of code in which it was detected. Also worthy of mention is the Micro Focus SAST 45 solution, also mentioned in Gartner's Magic Quadrant. Thank you for your kind attention. Bye. Hi, welcome back to this course on secure coding. In this lesson, I will talk about the OWASP community and the top 10 OWASP list of the main risks in the world of web applications. The OWASP community deals with various projects related to the security of web, mobile, and IoT applications, and the development of related tools and methodologies for security. This slide lists some of the main methodological and informative documents on web application security. You can find many interesting projects for the IT security world on the site, such as the Pentest Guide for Web Applications, or projects related to tools developed by the community, such as the OWASP ZAP. The top 10 OWASP of the main risks is a guide that the community has drawn up and that periodically updates, which illustrates what are currently the 10 most critical risks that can undermine the security of applications and web servers. Risks include issues related to a lack of validation of application input, vulnerabilities related to authentication mechanisms, and management of web sessions. They also detect risks due to incorrect implementation of access control authorization, incorrectness in the configuration of web server or application server, and also problems related to APIs and third-party components used without adequate security on the absence of vulnerabilities. They also detect risks on the insecure use of data exchange files, such as XML or JSON, identifying them under the XML external entities and insecure deserialization entries. Thank you for your kind attention. Hi there, welcome back to this course on secure coding. In this lesson, I will talk about the standards currently available and which we can inspire and follow for the secure coding of applications. Once again, an inexhaustible source of guidelines and best practices for the security of web application is the OWASP website. For example, we can find from OWASP the Software Assurance Maturity Model, in short SAM, a guide to improve the process the organization follows when building applications and APIs. OWASP also provides us with a manual of guidelines for the secure development of web applications. Another interesting repository with regards to secure coding guidelines is that of the SEI Software Engineering Institute of Carnegie Mellon University. It provides guidelines for secure coding in Java, C, C++, Android, and Perl. As for the development in .NET, the Microsoft site provides various materials for secure coding. And also for the development of applications for iOS on the Apple site, in the section dedicated to developers, there are guidelines for secure coding. And to finish, the CWE section of the mitre.org website shows the 25 main types of programming bugs that can be found in applications. Thank you very much for your kind attention. Hi, welcome back to this course on secure coding. In this lesson, I will make a brief introduction to the TCP and HTTP protocols. We see here the 7-level architecture of the TCP IP stack, with indication for the various levels of some important protocols. In the slide graphics, the typical onion encapsulation of the data in the various TCP/IP levels is represented to form the packets that pass through the LAN/WAN networks. Also here, an indication of some protocols present on the various TCP/IP levels, with an indication also of the security devices acting on the various levels. Let's now look at the classic layered architecture of a web system. Note the web client that communicates with a web server which redirects requests to an application server, which then retrieves data from a DBMS. This slide shows the typical architecture of CMS, content management systems, such as WordPress, Joomla, or Drupal, to underline the fact that the security of layered architecture is linked to the security of every single component of the architecture. Successful attacks always exploit vulnerabilities of weaker components. A web system in general may have additional architecture elements, such as an authentication server or an SMTP server for forwarding mail, but it is essential not to include components if they are not actually needed in order not to increase the attack surface without reason. Let's take a look at the TCP header and in particular the control flags bit that play an important role in establishing and closing TCP sessions. A TCP packet with the same bit set starts the TCP handshake, as we will see in a moment. Let's see how a TCP/IP connection is initiated. The client starts the handshake with the packet with the bit SYN set. So if the server is available to accept the connection, it responds with acknowledgement to the SYN packet, and then handshake ends with the ACK at the SYN ACK. Then the exchange of data begins between the client and the server. The data transmission then continues between the client and the server based on the application protocol established between the two. The example shows the case of the HTTP protocol, which is based on an exchange of messages between client and servers of the type HTTP request and HTTP response. TCP/IP connections end by sending a packet with the bit FIN set, and they can end with a request sent by the client or the server. The HTTP protocol is based on HTTP requests forwarded to the web server by the web client and consequent HTTP responses. We will soon see the structure of the request and response messages. A request and responses are structured in a similar way and consist of an initial line, 0 or more header lines, and an empty line and the body of the message, optional. The slide schematizes the structure of a generic request or response message. Let's see in the case of the request message how the initial line is structured. It is composed of three parts. The first is the HTTP command that you want the web server to execute. The second part is the resource web page that you request. And the third part is the version of the HTTP protocol with which you want to submit the request. Here are some of the HTTP commands most commonly used in requests, with an explanation of their use. Let's see, in the case of the response message, how the initial line is structured. Composed of three parts, such as the request line. The first part indicates the version of the HTTP protocol with which the server responded. The second, a status code that represents the category of the response. And the third is a description of the status code. Here are some of the HTTP header fields most commonly used in request header lines, with an explanation of their meaning. And here instead are some of the HTTP header fields most commonly used in response header lines. The body of the message, in the case of HTTP responses, consists of the HTML of the resource requested by the client. Or in the case of requests, it includes, for example, the inputs entered and sent with a POST method from the client to the server. Here is a complete example of an HTTP transaction with a request from the client and the related response from the web server. Thank you very much for your kind attention. Hi there, welcome back to this course on secure coding. In this lesson, I will talk about the OWASP Web Security Testing Guide. OWASP Web Security Testing Guide is a guide that deals with how to carry out ethical hacking activities on web applications. You can download the entire PDF guide from the OWASP website. It includes several sections such as information gathering, authentication, session management, input validation, each of which presents various tests that can be carried out. These, for example, are the possible tests to be carried out regarding the initial phase of the web application pen test, the preliminary collection of information on the target. Each test is coded with an identification code. For each test, there is a description of the purpose of the test or what it wants to achieve. You can also find a description of how to run the test and which tools you can use to execute the test. For each test, there is also a brief description of the possible remedies with respect to the vulnerabilities identifiable by the test. Thank you very much for your kind attention. Hi, welcome back to this course on secure coding. In this lesson, I will talk about the secure coding guidelines for validating application input. As a starting point for the discussion of input validation, I will base the discussion on OWASP's secure coding guidelines. First of all, it is necessary to understand what the possible input channels are for a web application. In this slide, I highlighted the various possibilities with which a web application can receive data inputs, because it is important that validation takes place on all possible input channels. The validation must include a phase of canonicalization of the data before validating them, or returning data to a standard format to avoid validation bypass with transcoding techniques. The validation must verify that the input data respect the expected format in terms of size, data type, range. For the search for input characters that underlie particular types of attack, It is always better to reason from a white list of hallowed characters rather than a blacklist of illegal characters. Also prefer the mechanism of regular expressions for the validation of input. In addition to validating the input of web applications, it is also important to make sure that the output of the application does not cause damage to third parties, such as a database with which the server-side application dialogues or web clients through responses. The lack of adequate input validation is the cause of a huge variety of possible types of attacks, of which the slide provides a list. Thank you for your kind attention. Hi, welcome back to this course on secure coding. In this lesson, I will talk about a classic attack resulting from a lack of validation of input, the SQL injection attack. SQL injection derives from the possibility of injecting malicious data into the form of SQL code using any input channel such as query string parameters sent via getHTTP method or fields of a data entry form sent via POST. The malicious SQL code changes server-side the legitimate query that the programmer wanted to do on the DBMS. By means of SQL injection, an attacker can even go so far as to recall system stored procedure and therefore directly interact with the server hosting the web application or the DBMS. The slide scenario illustrates the possibility for an attacker to bypass a possible login page by exploiting a vulnerability of SQL injection. As you can see, by injecting a malicious input, an SQL query is created that allows an attacker to bypass the login page. The attack techniques of SQL injection can make use of operators such as the union operator to determine queries completely under the control of the attacker, as can be seen in the current slide. Among the best remedies to counter SQL injection is to create parametric server-side queries, avoiding to concatenate data from inputs with constant pieces of SQL. In the slide, we see an example of a parametric query created in Java. Let's see the continuation of the parametric query example in Java. Here is also an example in C# of parametric query to avoid vulnerabilities of SQL injection. Here is where Ado.NET-based parametric query is created and executed. Incidentally, if link queue to entities or link queue to SQL is used to query databases, the problem of SQL injection does not exist. And here is another example of mitigation using a parametric query in a PHP web application. Some in-depth links on the SQL injection vulnerability. We can see here a list of best practices taken from the OWASP's Secure Coding Guidelines about DBMS security. For example, use a least privilege policy when accessing the database, or do not leave the connection string authentication credentials hard-coded in the source code. Some other best practices on database security, such as disabling any unused DB default accounts. Thank you so much for your kind attention. Hello, I will use the VVWA project from GitHub that shows the various vulnerabilities including SQL injection and then check how to mitigate them programmatically. Let's try the first laboratory on SQL injection. Let's you understand what the vulnerability consists of. I have set up a login page which allows a user to authenticate. Trying with wrong credential, you will not be able to enter. Sometimes you can tell if an application is vulnerable to SQL injection by simply injecting a single quote, which is a character that encloses alphanumeric data in SQL. The server-side query is created by concatenating parts of fixed SQL to SQL tied to user input. Then injecting the single quote, you can force to generate an incorrect SQL query. And this, if the server-side exceptions are not handled, it will allow you to view the details of the error on the browser. This may indicate the presence of the vulnerability in the server-side code. Now let's try to insert a classic SQL injection pattern that is or1 equal 1 for the username and anything in the password field. And we managed to enter the server section without knowing valid credential. So let's see now how you can mitigate the vulnerability programmatically. Let's go back to the source code of the login page and we comment on the vulnerability SQL query version and uncomment the parametric query version. Okay. And so this will have mitigated the problem. Now let's try to put the application back in execution and try again to inject the malicious pattern. So okay, but this time you see the authentication failed message, so the attack failed. And in applications where data access occurs through object relational mapping, such as in .NET through link queue to entities queries, the problem of SQL injection is already mitigated natively. This is because the values possibly deriving from a user input at the link queue query level will be natively considered as parameters. The problem we have seen can only exist with .NET PHP or in Java by creating non-parametric queries that link fixed SQL server side to user input. Hello, welcome back to this course on secure coding. In this lesson, I will talk about two types of attack resulting from a lack of validation of input data: the LDAP injection attack and the XPath injection attack. To frame the possible scenario in which an LDAP injection attack can occur, it is necessary to refer to applications that explicitly request access managed at the application level by the programmer from an LDAP server to retrieve information for authentication or other information. This scenario is typically linked to architectures based on Linux or Unix operating systems, in which an LDAP server for authentication is more easily found. In fact, in the authentication of web applications for intranet based on Active Directory, such as in Windows Integrated Authentication, LDAP queries are transparent by the programmer and managed directly by the operating system. If present, the vulnerability can have serious consequences, such as in the case of SQL injection, for example, a bypass of authentication without knowing the login credentials. In this slide, we see a typical example of LDAP injection for an authentication bypass. In the absence of input validation and assuming a server-side concatenation of the user input with constant parts of the where condition of the LDAP query, the example shows how you could get a query with a true where condition simply by knowing a valid username. The use of parametric LDAP queries and an input validation are, as in the case of SQL injection, the countermeasures to be adopted to avoid LDAP injection. In this scenario, the hypothesis is that server-side XPath queries are performed on XML data structures and that there is a lack of user input validation that allows you to create the XPath query server-side. Assuming that this XML file that represents a list of users is the object of the XPath query for an hypothetical authentication, we will see how, with a lack of validation, the XPath injection attack could occur. The slide shows how a vulnerable code could compose the XPath query server-side without validating the username and password values coming from user input. And the consequences, once again, with a malicious input could be to be able to obtain a where condition of the XPath query always to true with a consequent bypass of authentication. And once again, the solution in order not to introduce a vulnerability consists in validating the user input and, if possible, using parametric XPath queries. Thank you for your kind attention. Take care. Hi, welcome back to this course on secure coding. In this lesson, I will talk about a classic attack resulting from a lack of validation of input data. The cross-site scripting attack, in short, XSS. XSS derives from the possibility of injecting malicious data into the form of JavaScript code using an input channel such as query string parameters sent via getHTTP method or fields of a data entry form sent via POST. The malicious JavaScript code, not validated and therefore not blocked on the server side, is executed against a response going on the user's client. So, XSS is a type of attack that does no harm directly to the server, but to the user. XSS can be used by malicious attackers, for example, to steal session cookies from legitimate users and send the relative session ID to an attacker, or to redirect users of a site to login pages of a fake clone site in order to steal authentication credentials. The DOM-based type of XSS can occur when JavaScript code in a page does not suitably validate data that it can take as input. Here is an example of JavaScript code in a web page that is vulnerable to DOM-based XSS. The problem stems from the fact that the document.write function does not validate its argument before using it, allowing the injection of malicious JavaScript. The non-persistent type of XSS is typical of applications in which an input to the application sent via request is returned with a response by reloading the same page with a post back or on a different page. In the persistent typology, the non-validated malicious JavaScript is even saved in a database and then retrieved through queries and sent on clients. For the remedy to XSS, important before validation, normalize or canonicalize the data. The table shows the various possibilities of character transcoding that a malicious attacker could exploit to bypass a validation without canonicalization of the data. Among the possible remedies for XSS is the use of regular expression to search for the malicious pattern consisting of the tag script/script used to enclose the malicious JavaScript code that an attacker could inject. Here is an example of C# code that implements a remedy for XSS. And here an example of Java code that implements a remedy for XSS with regular expression. Some links for further information on the topic of cross-site scripting. Thank you very much for your kind attention. Let's see this laboratory using the VVVUA project downloadable from GitHub. It is a project developed in ASP.NET that provides various laboratories to test vulnerabilities and understand how to mitigate them. So we select the third menu item, Cross-Site Scripting Lab. Press the link. Okay, so press XXS Lab. And okay, we can now experience the cross-site scripting vulnerability. Suppose we enter a text in the text box and send it to the next page. The next page will receive the entered text and simply display it. We can see on this page that the previous text is displayed. Now, let's try now to insert something different. A very simple JavaScript code. That's the malicious pattern enclosed in tag script, which executes the alert function, which will display a window on the screen when executed. Okay. So, on the next page, I should see now if the application is vulnerable, the execution of the JavaScript code. And that's it. And here is the JavaScript code not blocked in input, is sent in execution. Let's see now how to mitigate the cross-site scripting vulnerability in the code. Let's go to the page that receives the data sent in post, is the page named XXS Elabas Pix C#. Currently, the code does not validate the data that comes from the previous page. And I'm going to fix with a solution that implements a validation through a regular expression. The solution also normalizes the data before submitting it to the regex, in order to avoid bypass by transcoding the input in a different char set of characters. Then the regular expression defines a pattern to be searched, and then if at least one occurrence of the pattern is found, the error message is printed. Vice versa, the validated data is printed. Okay. We should also comment this line of code. Okay, and now Let's start again the application and inject the same pattern, malicious pattern, and the injection was blocked. Hi there, welcome back to this course on secure coding. In this lesson, I will talk about another classic attack resulting from a lack of validation of input data, the OS command injection attack. The prerequisite for an OS command injection vulnerability to exist is that server-side, the application makes calls to the operating system through libraries, DLLs, components, or functions. Such calls to the operating system become vulnerable if they involve passing invalid input arguments. The slide shows a possible example of server-side invocation of a script which makes calls to the operating system to which parameters depend on user input are passed. Malicious inputs could, for example, be executed by server-side functions such as the C++ system function or the PHP exec function. Attackers may also make use of shell operators such as the pipe operator or the ampersand operator to exploit more efficiently the vulnerability from OS command injection. To test the presence of the vulnerability in black box mode, you can try to inject malicious inputs as a ping command that create a delay in the response of the web application. So if there is actually a delay, it means that the application is vulnerable. Remedies for OS command injection are to avoid calling OS commands directly. And if the use of OS commands is unavoidable, make sure to validate the inputs from the request to only a white list of possible values by discarding the rest. Furthermore, calls to system functions should be made with the least possible privileges. Thank you for your kind attention. Hello, in this laboratory we will experience the exploitation and mitigation of an OS command injection vulnerability. I have set up a very simple feature on this page. The user can select a type of data via the combo box, and by pressing the button, the value relating to the choice is displayed with a postback. Each type of combo box value corresponds to the display, when the page is reloaded, of an environment variable of the web server. For how the page functions and the values displayed, it can therefore be assumed that there is the invocation of some operating system shell command on the server side. So, command that reads and returns values of environment variables. So if you presume this, you can go on to test if an attack could be successful. Let's go to the Chrome Developers Tools and let's identify the combo box, the select tag in the DOM of the page. The select tag has three option elements with their values. Set to recall three server-side environment variables or commands. These are the echo username, date/t, echo cd, which are precisely three operating system commands. invoked server-side. Okay, so let's try to modify the value of the second option element. We replace the whoami command instead of the date/t command. And it displays the user's name. Or we can insert now the command here, and then we can see all the server-side content of the current directory. Okay, so let's try to see how to mitigate the vulnerability. Now, I remove the comment to a conditional switch block, which is used to check if the command you want to execute falls within one of the acceptable values. Otherwise, you exit the page load without doing anything. So, in practice, it's a whitelist of acceptable commands is created. Any other command not included is discarded. Let's try now to run the laboratory again with the mitigation. The page without malicious injection works as before. Okay. Now I activate the developer tools again, and now inject a shell command dir into the second option element as before, but this time trying to click the button to execute the injecting command, it is not executed. So thank you. Hello, welcome back to this course on secure coding. In this lesson, I will talk about two types of attack resulting from a lack of validation of input data: the local file inclusion and the remote file inclusion attacks. First of all, I would like to say that the LFI and RFI vulnerabilities are found much more frequently in web applications developed in PHP or Java than other technologies, due to the use that is made of the function include in these languages. Let's see some examples to understand where these vulnerabilities come from. Take the example shown in the slide. The PHP web page through a combo box allows you to select the name of a language, and when the page is reloaded, this name is used to generate the name of a file that is loaded via the include function server side. The vulnerability stems from the fact that the getLanguage variable is not validated before being used to determine the file name. So if an attacker values the value of the language parameter in the query string to a local path or to a remote URL, in the absence of validation of the parameter value, it opens the site to LFI or RFI vulnerabilities. Here we see another example of Java page vulnerable to LFI-RFI due to lack of validation of the path created by passing a parameter p to the page. In general, the remedy for these vulnerabilities consists in verifying the path that is determined through data input based on a white list of eligible paths, discarding any other path value that does not fall within the wide list of acceptable paths. Thank you for your kind attention. Hello, we'll see in this session the two laboratories related to local file inclusion and remote file inclusion. Let's start from local file inclusion lab. On this page, through the load button, the content of a static HTML page is loaded with postback to the page itself. So let's see which static page I refer to. The page that loads is the .lfi HTML with this static content you see. This page is inside the virtual directory of the web application. And this is a behavior that the programmer would expect, that is loading the content of this static page. If the vulnerability is present, what can the malicious attacker do? Malicious attacker can change the path value of the file to be loaded assigned to the ID parameter. Going to insert a local path inherent to a file present on the server, when the page is reloaded, its content is seen. In this way, the malicious attacker, knowing files in known position on the server's file system, could read the content at will. Okay. Let's see how we can remedy this vulnerability. Let's go to the source code of the page that processes the content of the static file, and we can uncomment a switch construct that verifies that the file to be loaded falls into a whitelist of admissible path. In any other case, the file is not loaded. Now, let's try to rerun the laboratory having applied the mitigation. And we should see that the access to unexpected files will no longer be possible. So let's see, I run the laboratory again, and I try again the malevolent injection of an illegal path, but as you can see, this time the attack is not successful, and the content of the illegal file is no longer accessible. We can also see a similar example for the remote file inclusion vulnerability. The programmer expects to load again the same static page, but in the form of a URL. The URL that the programmer expects is that of the application, but if RFI vulnerability is present, a malicious attacker could force the application to load the resource from a remote URL. So we can try to inject a remote URL and force the application to load that resource. And here is the result you can see now. Hello, welcome back to this course on secure coding. In this lesson, I will talk about secure file management and about an attack related to a lack of validation of files uploaded to web applications. Unvalidated file uploads is a very critical vulnerability for web applications, since if present, it allows an attacker in a very short time to upload, for example, a web shell on the server and take possession of it. The remedies in the management of upload files are reported in the best practices of the slide. Among the most important indications, check the type of incoming file before accepting it. Remember that checking the extension is not enough, but among the metadata of the file, check the so-called magic number consisting of the first 4 bytes of the header of the file that identifies its type. Thank you for your kind attention. In this session, we will see a workshop of the non-validated upload of files to web application and the possible mitigation. So, we can click on the Select File button, select a file, for example a JPG image, and send it to the web server with the Upload button. Going to the server, you can see that the file has arrived in the Uploads folder. The Uploads folder is in the application's virtual directory, and this is already a serious mistake. The upload function, however, is not developed correctly. In fact, it is possible to upload a file of a different type from that which the programmer expects to receive. For example, we can upload a PDF file, and in fact, we find in the Uploads folder the PDF file sent. The problem in the presence of this vulnerability could arise if the attacker, instead of uploading a harmless file, went, for example, to upload a web shell. The web shell is developed with the same technology as the web application pages. In this case, it is in ASP.NET language. The web shell arrives in the Uploads folder, as you can see. At this point, the attacker can load the web shell and run it. The web shell is made to run operating system commands on the web server. So, in this example of running the dir command on the server, now let's see what mitigation of this vulnerability consists of. It is necessary to ensure that it is possible to upload only the type of desired files, for example, JPG files, and to block the upload of any other type of file. I then go to extract and check the first 4 bytes of the uploaded file that indicate the type of file, and check with a switch construct if the 4 bytes extracted correspond to the value of the type of file that I expect. If there is no match, an error message will be printed, and the file cannot be uploaded. A check is then made on the size of the file that is uploaded, so that if it exceeds a set threshold, the file is not accepted. With mitigation applied, let's now try to rerun the laboratory. Okay. And I delete previously uploaded files, so let's try the lab again. Let's first try to choose an allowed file, an image, for example, and I find the image in the, okay, upload, and I find the image in the upload folder, so the upload was successful. But if I try to upload the web shell, this time I find an error message and the upload is blocked. Hello, welcome back. In this lesson, I will talk about another classic attack resulting from a lack of validation of input data, the buffer overflow attack. They are among the most lethal attacks because if they are successful, they allow through the establishment of communication channels towards the host of the attacker to make the attacker take possession of the attacked target. The buffer overflow vulnerability is typical of applications developed in C or C++, where the memory allocation of variables and data structures can be managed directly by the developer and where the use of pointers, if not correctly managed, allows the possibility of introducing this type of vulnerability. Two types of buffer overflow can occur, that is, memory stack or heap overflows. Entering into detail the mechanisms behind these two types of buffer overflow goes beyond the scope of this discussion. The example shows a very simple C program that shows how trivial it is to introduce a buffer overflow vulnerability. The vulnerability arises from the fact that when using the string copy function, it is not verified that the destination buffer is sufficiently large to contain the input data. In managed applications developed with object-oriented languages newer than C or C++, such as Java or .NET applications, it is not possible to have vulnerabilities from buffer overflow. In fact, the memory allocation of variables and objects passes through the garbage collector of the JVM or the CLR of the .NET framework. However, there are some exceptions that can lead modern applications to still have vulnerabilities from buffer overflow, as in the example of the slide, through the use of unsafe declaration in .NET that allows you to create a managed code, or if you use components or DLLs written with unmanaged code. In addition, Java applications, Android or .NET application can still be vulnerable from buffer overflow through vulnerabilities directly from the JVM or the CLR or from unmanaged libraries they call up. We see in this slide some recommendations to avoid introducing, mainly for C or C++ applications, buffer overflow vulnerabilities. I've shown in the following slide some examples of vulnerabilities from buffer overflow that have been discovered over the years. This in particular is a WhatsApp buffer overflow vulnerability inherent in the RTCP protocol used for VoIP calls. Here is another example of vulnerability from buffer overflow in Acrobat Reader. And another example of buffer overflow vulnerability in the OpenSSL library. And finally, an example of a vulnerability from buffer overflow in the Java virtual machine. Thank you for your kind attention. Hello, welcome back to this course on secure coding. In this lesson, I will talk about two types of malicious data injection, XML injection and XML external entities. The injection of XML as input, if not blocked by adequate validation mechanisms, can have serious consequences in terms of security, as we will see in the following example. The injection of malicious XML in this example results in an output XML file that would allow the creation of a user with administrator privileges instead of a normal user. So the remedy consists in validating the input, for example, with regular expressions, and blocking the possibility of inserting tags enclosed between less than or greater than symbols. Let's see this other vulnerability, the XML external entity vulnerability. The XXE vulnerability, linked to an exchange of data in XML format, occurs against a poorly configured XML parser. A purely configured parser can agree to extract and process data from an external entity instead of processing the data that should reside in the XML file itself. The major risk factor for the presence of this vulnerability is that the parser allows the definition of DTD in the XML document and allows the processing of external resources. Among the most important remedies, disable XML external entity and DTD processing in all XML parsers. As a remedy for XXE, it is also important to use an XML document validation based on XSD XML schema definition. Thank you for your kind attention. Take care. Hello, we will see in this lesson a laboratory concerning the exploitation of vulnerabilities of type XML external entities. In the VVVA application from GitHub, I developed this laboratory accessible through the XXE lab link, which allows you to understand what this vulnerability consists of and how it can be mitigated. In the text area, there is a hypothetical XML document concerning a CD catalog. And this is what the programmer on the next page expects to parse. So, by pressing on the process button, you can see that on the next page the XML is processed and its content is printed. Let's go back, let's see what happens if instead of sending the correct XML, you get an XML modified as follows. This is an example of an XML external entities attack pattern, the theory of which I explained in the previous lesson. And in this attack pattern, I have also prepared the possibility of accessing an external entity, specifically a file on the web server's file system. So, the XML parser, if purely configured, will load the data from the indicated path. So let's see then, with this pattern, making it process on the next page, what happens. And here it is, the parser is vulnerable and is being tricked into processing external entity data, the content of a file. So let's see now, okay, how to mitigate this problem. Let's go to Visual Studio, back, And okay, let's go to Visual Studio. In the source page of the page that processes the XML file here, and let's comment on the line of code that sets the DTD processing property to parse. Yeah. And I'm commenting the line that sets the property to the prohibit value. So that's blocking the possibility of parsing an XML that defines a DTD. So you can see the mitigation is very simple, but the important thing is to make sure what the default value of this property is. Now, let's go back to run the application after applying the mitigation, and let's see what happens if you try to inject the malicious pattern as before. So let's try as before to process the XML that defines a DTD. Okay, but this time, as you can see, the possibility of parsing the XML file is blocked, and the runtime exception is thrown, which I deliberately didn't handle to highlight the anomaly. So, thank you for your kind attention. Hello, welcome back to this course on secure coding. In this lesson, I will talk about insecure deserialization, a risk included in the OWASP top 10. Serialization is a process that involves transforming a collection of objects into a file typically structured in XML or JSON format. Deserialization is a reverse process of rebuilding the collection of objects from the XML or JSON data file. The whole process can be used to make heterogeneous systems communicate with protocol such as SOAP. We see in the graphics an example of serialization process. And in this graphic, the inverse process of deserialization without any tampering. The vulnerability arises if an attacker is able to tamper the XML or JSON structure and have it processed by the deserialization process. The tampering can consist of adding or removing entire new elements, adding or removing attributes, or changing attributes' values. Among the remedies to remedy this vulnerability, mention should be made of the use of the digital signature and the transmission of data by means of secure protocol, such as HTTPS. It is also recommended to deserialize to rely on standard, tested and validated components and libraries, and to do a type check when calling the method that deserializes. Other useful indications to counterattack risk include the use of a log and monitoring mechanisms for deserialization. Thank you for your kind attention. Take care. Hello, welcome back to this course on secure coding. In this lesson, I will talk about the possible mechanisms that can be set in a web application to implement authentication to reserved sections. Authentication is typically done by providing the application with an identification parameter a username, and a password or a PIN or a biometric credentials. By default, web servers do not implement authentication mechanisms, so access to resources is possible for anyone, and any authentication would be delegated to the application level. It is possible to implement an authentication delegated to the web server, and the simplest mechanism is basic authentication. The major disadvantage is that in this authentication mode, the credentials are not encrypted but are simply encoded with a base64 algorithm, which is reversible. Similar to basic authentication, but in this case, the credentials are subjected to hash algorithms, and through challenge response, it is possible to mitigate the replay attacks. With Windows integrated authentication, the authentication occurs on Active Directory through NTLM or Kerberos protocols, so it is more robust from a security point of view than basic or digest authentication. If you want to further strengthen authentication to prevent, for example, man-in-the-middle attacks, you can use multi-factor authentication, for example, based not only on username and password, but also on a one-time password generated by a device or a code received by SMS. The authentication delegated to the web server, basic, digest, Windows integrator, etc., has the disadvantage of not being suitable for public domain web application, but more typically for internet web applications. For web applications open to the public, authentication must be delegated to the application level. Here is an example of form-based authentication for a ASP.NET web form application set via settings in the application's web config. In the XML authentication element of the web config, it is defined which page, login aspects, should be redirected to if users try to access protected resources, and to request authentication for access to protected resources contained in a particular virtual directory. A web config of the directory can specify in the authorization element a denial of access for unauthenticated users. In the same way, in an ASP.NET MVC application, it is possible to define which should be the default controller and action method to which authentication should be delegated if the user tries to access protected resources. This is a login action method that implements the authentication for the ASP.NET MVC application. And here is an example of how to define in an ASP.NET MVC application which controller or action method require or not authentication, using, for example, attributes authorize and allow anonymous. Something similar to what we have seen for ASP.NET MVC applications can also be done to implement authentication in MVC applications developed with Java and Spring Framework, as you can see in this example. And in the same way, it is possible to implement an application authentication using the potential of the framework also in PHP web applications developed, for example, with Cake PHP. In the case of enterprise systems in which you want to implement single sign-on authentication mechanisms or having a heterogeneous client, you can use, for example, the OpenID Connect protocol based on OAuth 2 that use an identity server on the cloud for the authentication. Thank you for your kind attention. Take care. Hello everybody, welcome back to this course on secure coding. In this lesson I will talk about the OWASP guidelines regarding the implementation and configuration of authentication and password management. Among the indications to be mentioned, for example, the fact of keeping the authentication logic separate from the reserved pages to be accessed through redirect mechanisms, and also archive the password hash and never clear text passwords, preferably using robust hash algorithms, never give indications about which component of the credentials was wrong in a wrong login, enforce robust passwords choice mechanisms with appropriate minimum length and complex character alphabets. And also pay attention to password reset mechanisms, which, if weak, can allow an attacker to obtain user credentials. Temporarily disable the normal user after n incorrect login attempts. Implement adequate password change policies. In cases of critical applications, use multi-factor authentication mechanisms. Thank you for your kind attention. Hello, welcome back to this course on secure coding. In this lesson, I will talk about possible scenarios of attack on authentication mechanisms. The greatest risk to authentication is that someone manages to sniff network traffic and thus intercept authentication credentials. Some countermeasures typically used to remedy this risk are shown on the slide. Among the attacks most commonly used to intercept data traffic on LAN networks can be mentioned ARP poisoning, DNS poisoning, use of rogue DHCP server. A tool that can be used for assessment on LAN and see if it is potentially attackable by the aforementioned man-in-the-middle attack techniques is the Bettercap tool. Another typical attack on authentication mechanisms is a brute force attack or dictionary-based attack. Also in this case, the typical countermeasures for these types of attacks are reported in this slide. The slide shows a screenshot of the use of the Hydra tool, which can be used to make brute force attacks or dictionary attacks on various protocols that require authentication, including SSH, RDP, FTP, etc. And finally, the slide shows various tools that can be used to crack password hashes once they are available. Thank you for your kind attention. Welcome back to this course on secure coding. In this lesson, I will talk about the mechanisms implemented by web applications to manage sessions. Session management is essential in web applications since the HTTP protocol is stateless, and therefore applications need to implement mechanisms for the persistence of status information such as successful authentication. Where possible, from a security point of view, it is preferable to rely on management mechanisms of the sessions implemented and offered by the application frameworks. The importance of session management is shown in this slide, where it is seen that in the absence of state management, access to reserved resources would provide for a continuous request for authentication. Session management normally uses various techniques, which range from the use of cookies to session variables related to the user or to application variables global for all users. Or you can use parameters passed in query strings from page to page. The table summarizes the various possibilities distinguishing between server-side or client-side state management. We see here a classic life cycle of creating an authenticated user session, which makes use of an authentication cookie containing a unique session ID and associated with the authenticated user. After successful authentication, the server generates a session ID associated with the user, stores it server-side in memory or on DB, and then generates a cookie that contains a session ID and sends the cookie to the client. The client can then access the reserved resources by simply sending the authentication cookie to the server each time. The server will read it and verify that the session ID matches the one saved. At the end of the session, due to timeout or following user logout, the session cookie is invalidated. The session ID server-side is removed, and therefore user access to a reserved resource will result in a request for a new authentication. In the case of mobile web applications that dialogue with Web API or with REST services, we generally speak of stateless authentication, and the session is not managed through a cookie generated by the server, but through the sending by the client of an authentication token to each request for access to reserved resources. So thank you for your kind attention. Take care. Hello, welcome back to this course on secure coding. In this lesson, I will talk about safety guidelines in session management. Among the most important indications, it is worth mentioning the fact that wherever possible, the built-in functionality of the application framework should be used for session management, in particular for the generation of the session ID. The session timeout should be commensurate with the riskness of the application, long for low-risk applications, short for critical applications such as home banking applications. It is also important to change the session ID of the unauthenticated user after authenticating, thus generating a new session ID in order not to open the site to the session fixation attack. It is also important to use anti-forgery tokens to counter cross-site request forgery attacks, and also set the HTTP only and secure attributes for authentication cookies. As for WAPT on session management, the OWASP tests of the security testing guide relating to the chapter on session management can be implemented. And finally, some useful in-depth references regarding the best security practices on session management. Thank you for your kind attention. Bye. Hi there, welcome back to this course on secure coding. In this lesson, I will talk about a type of attack that exploits a vulnerability in the management of web sessions, namely the cross-site request forgery attack. The attack consists in exploiting with cross-site scripting or phishing actions for example by email, the persistence of an active session for a user of a given web application to make the user perform actions without his knowledge. In this example, assuming that the user has a valid session still active on an example.com site, if he visits a page of a malicious site with the tag displayed, the user may find himself changed without his knowledge the password on the example.com site. So, a first measure of contrast to cross-site request forgery is to ask, before performing critical operations, the user to provide an authentication parameter, a PIN, a code, etc., without trusting that the user already has a valid authenticated session not expired. Another remedy for cross-site request forgery is to use the so-called anti-forgery tokens codes, which can be activated with the application framework by means of appropriate settings in the pages that must transmit critical data with forms. In addition to the data fields, the forms will present a hidden field inherent to a token generated by the server that the client will have to send identical to the server. If the request does not present the token or does not match the one generated by the server, the request will not be processed and an error will be generated. You can find more information on cross-site request forgery on the OWASP website. The OWASP website offers many insights into this issue. So, okay, with this lesson, I end here, and I would like to thank you for your kind attention. Hello, welcome back to this course on secure coding. In this lesson, I will explain what are the main types of cryptographic algorithms that guarantee confidentiality and which indications of secure coding to follow regarding encryption. The need to satisfy the confidentiality requirement is required by legal regulations such as the GDPR, but also by various quality standards such as the ISO 27001. Cryptography is used in application development as a tool in addition to authentication to ensure the confidentiality requirement on data. Modern cryptographic algorithms can be divided into two large families, namely symmetric or private key algorithms and asymmetric or public key algorithms. We will see in the next lessons the working principle of these two types of algorithms. Let's see some guidelines for using encryption in applications. First of all, make sure that the cryptographic libraries used at the application level have been validated by security standards such as the FIPS 140.2. Another key aspect is the protection of private cryptographic keys used in applications. The question arises of where to store and how to protect them from unauthorized access. There are various solutions depending on the criticality of the application, including, for example, the use of ad hoc hardware for key storage, such as a trusted platform module, whose access is mediated by the operating system. Thank you for your kind attention. Bye. Hello, welcome back to this course on secure coding. In this lesson, I will explain the working principle of symmetric or private key cryptographic algorithms. The operating principle provides that symmetric cryptographic algorithms use the same key for both cryptographic and decryption actions. The cryptographic key length for symmetric algorithms today must be not less than 256 bits for a reasonable protection against brute force attacks. Symmetric algorithms are used in the encryption of data residing on local repositories, such as data on smartphones or data residing on users' laptops. If they were to be used to encrypt data in transit on a channel, the problem would arise of how to get the symmetric key to the other side of the channel, because if the key is intercepted, the confidentiality of the data is lost. The slide shows the operating diagram of the Advanced Encryption Standard algorithm, which consists of encrypting the data in bit blocks, performing byte substitutions, shift of rows, etc. on the blocks according to the key. The same sequence of operations done in reverse on the encrypted data according to the key allows you to get the data back in clear text. So thank you for your kind attention. Bye. Hello, welcome back to this course on secure coding. In this lesson, I will explain the working principle of asymmetric or public key cryptographic algorithms. Asymmetric cryptography is mainly used in the transmission of data on the channel, solving the problem of the interception of the key of symmetric algorithms. Each subject that must transmit on the channel has two cryptographic keys, a public key and a private one. There is a mathematical relationship between the two keys, but the knowledge of one key does not allow to know which is the other. Only the public keys of the receivers travel on the channel, which even if intercepted, do not allow data to be decoded. So if Bob wants to transmit encrypted data to Alice, he uses Alice's public key to encrypt the data, and then he transmits the data on the channel. Then Alice uses her private key to decrypt the data at the destination. To have a good strength against brute force attacks, asymmetric algorithms must use much longer keys than symmetric algorithms. We speak of at least 1024 bits. Using in the cryptographic action, in addition to the public key of the recipient, also the private key of the sender, you also get a guarantee of the authenticity of the sender. During the decryption phase, therefore, not only the recipient's private key will be used, but also the sender's public key. But how do public keys travel on the channel? Usually through digital certificates of the respective owners of public keys. Digital certificates are issued by certification authorities which certify the authenticity of the data contained in the certificates. X.409 is one of the most used standards for digital certificates. In addition to the public key information, the digital certificate contains other informations, such as the period of validity, the name of the owner of the certificate, the certification authority that issued it, etc. The certification authority that issues the certificate obviously also provides the applicant with the corresponding private key, which will be saved on the endpoint that will have to perform the decryption action. The digital certificate is also digitally signed by the certification authority so that its authenticity can be verified at any time. Which algorithms are then used in data transmission protocols on channels such as HTTPS or SSH? The answer is simple. An asymmetric algorithm such as RSA is used only in the initial handshake phase to transmit the symmetric key of an algorithm such as AES, which will then be effectively used for data transmission. This is because if only asymmetric algorithms were used for data transmission on the channel, using them long keys, they would result in less efficient data transmission in terms of time and amount of data. In this slide, we see the scheme of the working principle of the RSA algorithm, which it uses prime numbers for the values of the private and public keys, and the cryptographic operation is based on a modulo operation. Thank you for your kind attention. Hi there, welcome back to this course on secure coding. In this lesson, I will talk about hash algorithms. Hash algorithms, starting from variable length input data, generate a fixed length bit sequence called hashcode or digest of the data. And even just changing a single bit of the input data generates a completely different hash code. The hash algorithms are unidirectional in the sense that from the knowledge of the hash code, it is not possible to trace the data that generated it. The main use we make of hash algorithms is to guarantee data integrity. In fact, by generating the hash of any data, a file, a directory, an entire disk, it will always be possible to prove subsequently whether the data has been altered or not, simply by recalculating the hash and comparing it with the original one. Hashing algorithms are also widely used to store passwords in local data stores. In fact, passwords must never be saved in clear text, but the hash must be calculated and saved in the data store. The use of MAC, message authentication code, or HMAC, hashed message authentication code, can guarantee not only data integrity but also authenticity, so they are used in the handshake phase of data transmission protocols. We see in the slide some famous hash algorithms. Today, the SHA-2 with 512-bit digest should be used, since the others have proved obsolete, crackable in reasonable times, that is being able to trace the hash back to the data that generates it. SHA-2 also minimizes the collision domain, the probability of finding two or more different data that generate the same hash code, an event that cannot be eliminated but which can be minimized, also, for example, by releasing for the same data hash code in different formats, MD5 plus SHA-2, for example. In this slide, we see the block diagram of the SHA-2 hashing algorithm. Divides the data into blocks of 1024 bits, calculating for each block a partial hash up to the calculation of the final hash, which will depend on the calculation of all the partial hashes calculated on the blocks prior to the last, so that the calculation time is proportional to the size of the data whose hash is to be calculated. The slide instead reports the working principle of the digital signature of documents. The hash is calculated on the original document and encrypted with the asymmetric encryption with the signer's private key. Whoever receives the document can then verify both its integrity and the authenticity of the signer, deciphering the hash with the signer's public key and recalculating the hash of the document and verifying that it coincides with the deciphered one. A few words at the end of the lesson on the use of cryptography in applications. It is important to rely on the use of cryptographic libraries offered by the development framework and which have passed the screening with respect to security standards. The most important development environments offer libraries for the use of cryptographic and hashing algorithms. The slide reports the case of such libraries for .NET. But the same goes for those who develop in Java or other languages. And finally, some insight into the use of encryption at the application level. Thank you very much for your kind attention.